All right, so welcome everyone back to the GADEP's seminar. So today we are very happy to have Payman Eskandari, who will talk about mixed motives with large unipotent radicals.
Thank you very much. Thanks to the organizers for the invitation. It's a pleasure to be here. Although it would have been more pleasure if I was actually in Brazil. So I'm going to talk about a joint project with Kumar Murty. So let me start with some background here. Suppose you have a smooth projective variety over C. Actually, let's just say you can ignore the word projective there. Suppose you have a smooth variety over a subfield of C. Now, to this variety, for each degree cohomology, there's different cohomology groups attached to it. So the different cohomology theories. So you have a singular, in particular, you have singular cohomology, which is with coefficients in Q. So here you think of X as a complex manifold, and then you take the singular cohomology with coefficients in Q. And then you also have the algebraic de Rham cohomology. So the Rham cohomology from differential topology. So that's a smooth de Rham, but there's also an algebraic de Rham cohomology that. So this is due to Grothendieck definition of this, construction of this. So this is actually defined. It's a vector space over K, of the same dimension as the singular cohomology. Now we have the period pairing, which is the nth cohomology, the Rham cohomology, pairs nth the Rham cohomology and nth singular homology, and it's simply integration. So if I have a topological chain gamma, and then I have a differential form omega, I just integrate omega over gamma. So here, this algebraic de Rham cohomology, this intuitively, roughly speaking, this is just a space of differential closed algebraic differential forms, n forms. So this is sort of like this is a restriction. So for those that are not so familiar with algebraic de Rham cohomology, this is a restriction of the classical integration pairing between smooth de Rham and homology, and singular homology. Now, remember that in this setting, this is a vector space over K, now K being subfield of C over which X is defined. And so the numbers that you get here, the image of this map is going to be a K vector space, and we're going to call those the numbers in that image the periods of Hn of X, of the nth degree cohomology of X. So in this talk, every time I use the word period, it's in this sense. It's in the sense of the pairing between algebraic de Rham and singular cohomologies. Now, algebraic cycles. So for this, the word projective I put there because I wanted to mention this algebraic cycle. So up to here, you don't need the projective thing, but this algebraic cycles, if I add the word projective there, algebraic cycles on X and powers of X, they lead to relations between periods. It's an algebraic relations between periods. And then Grothendieck's period conjecture, the rough version of it is that, which sort of explains the intuition behind it, is that any algebraic period relation should come from geometry. So geometry leads to relations, and the conjecture is that all relations should come from geometry. Now, let me try to make this conjecture more precise. So now we're going to use some sort of jargon here, but I'll explain what they mean roughly. Suppose you have a Tannakian category of mixed motives over K, and K being C. But by the way, sorry, this K here was an algebraic subfield for us to have this conjecture. Now, suppose you have a Tannakian category of mixed motives over K. Again, algebraic subfield of C. Now, I have to say something. I should say something about these two words, Tannakian and a mixed motive. So a mixed motive is sort of very intuitively speaking, we want to think of it as a piece of cohomology of a variety. a variety over K here. Now, the point is that you have various realizations attached to a motive, a mixed motive. There's a Berry realization, the Ram, Eladik, and for this particular talk, it's Berry and the Ram that play an important role. Berry is the analog of is like the singular cohomology. So in the case that you're dealing with Hn of a variety, this would be simply exactly nth degree cohomology, singular cohomology with coefficients in Q. And then the de Rham realization would be, in that case, the algebraic de Rham cohomology. But the point is that this one is a Q vector space and this one is a K vector space. And again, you have in general this period pairing between the Ram realization and the dual of the Berry realization. And the numbers in the image, again, you're going to call them the periods of this mixed mode. Now, there's also this, so the Grothendieck period conjecture is going to be a statement about the transcendence degree of the field generated by the periods of a mixed mode. Now, that is supposed to somehow, you want to say that you want to relate that to geometry, right? So now that's where this word Tannakian comes into the picture. So Tannakian category is a category which is abelian, it's Q linear, there's a tensor structure, you have duals there, and double duals there's canonical isomorphism between each object and its double dual. So it's the same. It's a category that has the same properties as the category of finite dimensional representations of a group. And in fact, there's this duality theorem that says that any Tannakian category is equivalent to the category of representations of an affine group scheme over Q. Now, so here, for the purpose of, so let's go here. And now, so this Tannakian formalism allows you to associate to each motive M an algebraic group, which is called the motivic Galois group of M. So this is an algebraic group over Q. It's a subgroup of the general linear group of MB, the Berry realization. And it's controlled by the geometry of M. Yeah? Now, I'll say more about how this group is defined, but the statement of Grothendieck's period conjecture, the precise version is that if you have a motive which is defined over an algebraic subfield of C, then the transcendence degree of the field generated by the periods is the same as the dimension of this motivic Galois group of M. So this side you have periods, and then on this side you have a dimension of this group, which captures the geometry of M. Now, a few more remarks that I want to make here is that, so for the purpose of this talk, you can really think of a motive in terms of its realization. So think of a motive as a system of realizations, all of this data, which comes from geometry. And this group here, which is defined using Tannakian, formalism. So nowadays, there's actually a Tannakian, the theory of motives for a very, very long time was highly conjectural. There was no really good candidate for the category for the Tannakian category of mixed motives. But nowadays, that's no longer an issue. So, due to the work of Ayub, there's actually a geometric. There's a Tannakian category of mixed motives, which really, it is really, it's constructed geometrically. So morphisms, in some sense, do come from algebraic cycles and correspondences. So really, this group is actually now, does actually, come from geometry now. Now, let me tell us, how this group is characterized, because so far it's been some, mysterious black box. It's characterized by the following property. So you have this motive M. You look at the full Tannakian subcategory generated by M. So this is the smallest subcategory which contains M. Contains the unit object. There's a tensor product, so there's a unit object. It contains M, the unit object, and it's Tannakian. Yeah? So essentially, it's it contains M and the unit object, and has to be closed under taking direct sums, subquotients, tensor products, and duals. Now, if you take any object in the category generated by M, so you have the Berry realization of that object and the motivic Galois group of M, there's a natural action of this motivic Galois group on that Berry realization. And these actions are compatible with morphisms. So if I have a morphism between two objects in this category, then the induced map between the Berry realizations is equivariant under the actions of this group. So you get a functor from the category of the category generated by M and representations of this motivic Galois group. And in fact, that functor is an equivalence of categories. So that's the key property that characterizes this motivic Galois group. So you can think of the category generated by M as the category of representations of this group. And by considering the natural action of the group on actually MB, the realization of M itself, you get an embedding of this group into the general linear group of MB, and that's how you think of this as a subgroup of them. Any question about this slide? So you can just interrupt me if you have any questions. Now, so the period conjecture, precise version of it is that the transcendence degree of the field generated by the period is the same as the dimension of the motivic Galois group. Let me make a few comments about this. First comment that the conjectural part of this equality is the greater than or equal to part. The fact that it's the transcendence statement that the transcendence degree is at least this much. The upper bound portion is not actually hard to prove. There's a very standard argument for it. That's one comment. Another comment I should make about is about this asterisk thing. So, there's sometimes, a second part included in the statement of Grothendieck's period conjecture, some connectedness assertion, which, for the purpose of this talk, I'm not going to, talk about that. I'm just going to refer to this as the period conjecture. Now, one other thing that I want to say is that, this statement looks very, abstract, and, one may think that this formulation was done, after Grothendieck, much after Grothendieck, because at the time of Grothendieck, of course, there were no, there was no motivic Galois group really. So, but it's actually interesting to know that that's not quite the case. So, for historical notes, I encourage everyone to, have a look at André's letter to Christiana Bertolin in a recent paper of hers titled Third Kind Elliptic Integrals and One Motives in Journal of Pure and Applied Algebra. So this is as an appendix, there's there's a letter of André where he talks about the history of the period conjecture. And this is a page from that article, and I have highlighted some sentences here. So these are this is André saying this. He says in order to express appropriately his intuition that algebraic relations between periods should come from geometry, Grothendieck uses his idea of motives and motivic Galois theory. And then there's this footnote here that he says this statement is not just a conjecture in the history of mathematics. And then he says that a decade ago in Montpellier, he had the privilege to consult some unpublished notes by Grothendieck and motives, and the notes are available online. And he saw that he really wrote the period conjecture essentially as formulated, as we formulated. So I went to this page. There's a lot of notes there, and they're the ones that I looked at. They were handwritten, so I think it's very interesting to just go to that page just for historical interests, even just to take a look. I did I looked at these chapters and the issue. I was I wanted to get Grothendieck's handwriting himself, stating the conjecture, but I wasn't able to find like one single statement, but the conjecture, if one looks at those notes, the conjecture is really there, essentially in the same language that we have formulated it. Even though this side of it at the time was completely, it was just a yoga thing basically. There was no concrete definition or unconditional definition. Okay, so now let me give some examples here. Let's start with H1 of GM, of the multiplicative group. So this, if you think about the associated complex manifold, this is GM is C star, C minus the origin. you're looking at H1 of that, and this, which is the same as H2 of the projected line. So this motive is denoted by Q minus 1. It's usually called the Lefschetz motive. Now, well, H1 of C star, that's one-dimensional. Is a basis for the for the singular homologies given by this gamma, this loop gamma around the origin, and a basis for the de Rham realization is the differential form dz over z, and the period pairing would give you between these two gives you 2 pi I. Now, so this is one period of M to get. I mean, the K. Well, we're thinking of this as a motive over a Q, and the Q, span of this would be all the periods of this motive. Now, but the point is that the field generated by the the field generated by the periods will be the field generated over Q by this 2 pi I. Now let's look at the motivic side, the motivic Galois group side. So now the motivic Galois group of Q minus 1, it's easy to see that it's GM. So this is one-dimensional, and remember this is going to be a subgroup of GL of the Berry realization. So it'll be a subgroup of GM, but in fact in this case it will be, it's easy to say it's equal to GM. And so now the Grothendieck's period conjecture predicts that 2 pi R or pi has to be transcendental, which we know is true. So in this case, the period conjecture is no. Another example, let's look at H1 of an elliptic curve over Q bar. Now, the motivic Galois group is a subgroup of GL of the Berry realization. This is a two-dimensional rational vector space, so it's a subgroup of GL2. And then it's not difficult to see that there are two cases depending on whether E has CM or doesn't have CM. It'll either be a two-dimensional torus or will be all of GL2. So the dimension will be either 2 or 4, depending on whether or not you have CM. Now, in this case, there's a theorem of Chodnovsky proved by transcendental methods that says that the transcendence degree of the periods of an elliptic curve over Q bar is at least 2. So putting these, this together with the fact that I said the upper bound portion, was easy to prove, you see that Chodnovsky's theorem implies that the period conjecture holds in the CM case. The transcendence degree in the CM case is actually equal to 2. In the non-CM case, period conjecture is open in this case. Let's look at some mixed examples. So I used this word mixed before too, but I didn't explain, what it means here. So this mixed is in contrast with pure. So if you look at cohomology of nth degree, if you look at nth degree cohomology of a smooth projective variety, there's a Hodge decomposition there. There's a Hodge. So the singular cohomology comes with a Hodge structure of weight n. If the nth degree weight will be n. If you remove the smoothness or projectiveness hypothesis, then there'll be a weight filtration, and this filtration doesn't have to split, and then if you have multiple weights, that's where this word mix comes into the play, and especially if your weight filtration doesn't split. So if your object is not a direct sum of pure objects. Now this talk is really about the mixed objects. So let's look at some mixed examples here. Now remember we talked about this object Q minus 1, which was H1 of GM. Now Qn is the nth tensor power of Q1, and Q1 is the dual of Q minus 1 here. Now, so this is an object that has weight minus 2n. Okay? Q minus 1 has weight 2, and this has weight minus 2n. Now, x1 of the unit object by Qn carrier of mixed motives. This is by work of Blavatsky and Borel. One knows that this is zero if n is even or less than or equal to 0. And then if n is odd, so the fact in this even case, the fact that this is 0 in the even case has to do with the fact that the values of the zeta function and even integers, even positive integers, those are powers of pi. Now, if n is odd and greater or equal to 3, this X group is one-dimensional. And then we're missing one case, namely when n is equal to 1. And in this case, this is going to be Q star tensored with Q. So in this case, these are generated by Kumar motives. I'm going to talk about this in a second. Now, oops, sorry. Okay, so this is in general, when it comes to extensions and category of mixed state motives over number fields, there's conjectures for what these things should be, but in the case of extensions of one by these Tate objects, these are actually theorems. So this is not conditional here. Now let's look at what happens. Okay, so there were two interesting cases when n was odd, greater than or equal to 3, or n was 1. Let's look at n being odd and greater than or equal to 3. Now, the X group in this case was one-dimensional, and if M is a non-trivial extension of 1 by Qn, by Deligne and Goncharov, one knows that the period matrix of this M looks. If you take bases with respect to corresponding, with respect to appropriate bases, the period matrix looks like this. So it's a power of 2 pi I minus n coming from this Qn. See, remember Q minus 1, the period was 2 pi I, and Qn, the period will be 2 pi I minus n, and this is contained in M. And if you take your bases, nicely, then you're going to get this 2 pi I to the power of minus n in this entity, which comes from there. And there's a 1 here. And then the really interesting entity is this one, which is up to the power of 2 pi I is zeta of n. And remember, this n is an odd natural number. Okay, so the periods are 2 pi I, well, up to powers 2 pi I and zeta of n. Now, let's look at what happens with the motivic Galois group. See, remember that we said that this motivic Galois group of M acts naturally on every object of the category generated by M. So in particular, it's going to act on every object of the subcategory generated by this guy. And so you can just restrict that action. That's going to give you a surjective map from motivic Galois group of M to the group of the associated graded with respect to the weight filtration of M. And then the kernel of this, let's call it a U upper script mod M. Now, remember that the action of motivic Galois group is compatible with morphisms, respects morphism. So in particular, it's going to respect the weight filtration. And so this group is going to be contained in the parabolic subgroup of MB with associated to the weight filtration. So in other words, automorphisms of MB which preserve the weight filtration. If you take your bases appropriately, nicely with respect to the weight filtration, this is just the upper triangular, invertible upper triangular matrices. And then, again, by the same token that, the action has to respect, the categorical structure, this would be contained in the, in the product of GLs of the graded pieces. And this restriction map here is the restriction to the diagonal entries, to the diagonal. And then the kernel of this map is those matrices that have ones on the diagonal. Now, in this particular case, we're dealing with the 2x2 matrix because, this motive is two-dimensional. But the argument, the things that I just said actually, about this particular diagram hold in general about any motive. But in this particular case, so this thing here would be, you have 1, 1, and then there's a star there. This is the additive group. And so this would be a subgroup of GA. And, well, you're in characteristic 0. So your mode is either 0 or the additive group. Now, it's because the category generated by the associated gradient is semi-simple. So the category generated by pure motives, that's a semi-simple category. This is a reductive group. And this thing here, on the other hand, M itself was a non-trivial extension. So that tells us that this can't be equal to this. So this is non-zero, and well, so that tells us that this has to be the additive group. Now, so if you look at the dimension of the motivic Galois group, there's this here. Well, this is just GM. This is essentially our first example. This is GM, and then so dimension of this will be 1 + 1, 2. So now the period conjecture asserts that a dimension is that the transcendence degree of the field generated by the periods is equal to 2, or in other words, 2 pi I and zeta of n are algebraically independent over Q. So this, this example already shows how deep and powerful this Grothendieck period conjecture is. That by just looking at these two-dimensional motives, you're getting very strong, very deep conjectures here. So in particular, this implies that zeta of n has to be transcendental. So that was when you were working with n being odd and greater than or equal to 3. But now what happens if n is 1? So you're looking at extensions of, going back here, extensions of the unit object by Q1. Now in this case, so we said that the X group is Q star tensor with Q. So how do you get those extensions? So these would be H1s of these are relative cohomologies now. H1 of Gn, and then relative to 1, R, the set where R is a rational number greater than 1. And there's a Tate twister tensoring with Q1 to make the weights what they should be. And now, well, you can think of this in terms of the lens 1 motifs 2, but these are the non-trivial extensions of 1 by Q1. And the period matrix of this object here, okay, so there's going to be, from this 1 and Q1, you're going to get this 2 pi I minus 1 and then 1, but there's, again, this interesting entry here, which would be obtained by integrating 1 over z over the path from 1, straight line path from 1 to R. So this is an element of actually the dual of this guy here, because it's working with relative cohomology. And then this integral is log R, and then because of that Tate twist, I have to put a 2 pi I minus 1, but we can ignore that power of 2 pi R. The point is that we get basically a pi and a log R. And then by the exact same argument that we gave here, nothing changes. The motivic Galois group here is two-dimensional. So you see that in this case, the period conjecture predicts algebraic independence of pi and log of R. So these motives are going to appear again in the talk, but let's keep going. Now,
I'm sorry.
Yeah.
Just a silly question about this slide. Do we know that every extension of 1 by Q1 is of this form, or?
Do we know that every extension of well, we have to look at their Yoneda sums as well. They're generated by these things.
This is proved. This is a theorem.
This is
Okay.
Yes. The fact that those exactly, yes, that's so. Yes, so see, it's a theorem. So this is work of Blavatsky relates this X group to K theory, and then K theory groups for Q are related to well, they're computed by Borel. So this is actually equal to this, and yes, it's generated by those Kumar motifs.
Okay.
Yeah. Well, as yeah. Okay. So let me keep going. So let's talk about the unipotent radical of the motivic Galois group. So this is what the talk is really about. So this is the same diagram as we had before. This is, here M is actually now M is any mixed motive, and you have this sequence. This is a reductive group. This is the this is the unipotent radical, and you've got these inclusions here. This being the unipotent radical of the of this parabolic subgroup with respect to the wave filtration. Now, okay, so you can look at the adjoint action of the adjoint representation of the motivic Galois groups. It acts on its own, its Lie algebra, and this being a normal subgroup, so this is going to act on the Lie algebra of this. Okay, so let me give a name to the Lie algebra of this group. I'm going to call it lowercase u mod of M. Now, this group is acting on this, and then remember we had that equivalence of categories, coming from Tannakian formalism. So this action of this on this gives us a motive, which I'm going to denote by an underlined U mod M. I'm just going to call it UM throughout the talk, just so it's easier to pronounce. So it gives us a motive UM. This comes from Tannakian formalism. But now, see, because of this inclusion here, the Lie algebra of this is contained in the Lie algebra of this, which is strictly upper triangular matrices. You can think of it as that. More sort of more conceptually is the space of endomorphisms of M. So these are like just linear maps, endomorphisms, which send which drop the weight filtration. So they send Wn of M to Wn minus 1 of M. So that's of course stronger than just respecting the weight filtration. Now, so this is W minus 1 of NM, and then there's also you can again there's a motive attached to this, which I'm going to denote by this underlined thing. So this is the internal harm in this category. So think about category of representations. There are if you have two representations, there's a harm representation. Right? So this is that object. Right? You can ignore these things. Think of them as just linear maps, but remember there's an action of some group there as well. Now this inclusion here is compatible with the actions, and so this is the submotive of this W minus 1 and M. Now. We're going to say, so this is always contained in here, and we're going to say that M has a large unipotent radical if U of M is actually equal to W minus 1 of N of M. So we'll say M has a large unipotent radical if it's if it's okay. So the unipotent radical has an obvious upper bound, namely if this namely this thing here, and you're going to say that M has a large unipotent radical if that upper bound is actually achieved. Now, such motives are interesting, because of their periods. So, so in view of the Grothendieck's period conjecture, if I look at all motives, if I fix the associated graded and I vary the motive, so I'm looking at all motives, all mixed motives which have the same associated graded. So now this is being fixed, and this is changing here. So this would be the largest when this is as large as possible, and then in view of Grothendieck's period conjecture, what we see is that between all motives that have the same associated graded, these motives that have a large unipotent radical are the ones whose periods should have the highest transcendence degree. So that's why we're interested in these motives. Now, let's see what happens here. In some cases, it's very easy to see to characterize when a motive has a large unipotent radical. The easiest case is when when your motive is an extension of the unit object by some pure object of some pure object. And if the weight is positive because of weight consideration, so on and so forth, the extension has to split. It's not interesting. So that's why there's this negative condition here. So suppose your M as an extension of the unit object by some pure of negative weight, and suppose this L is actually simple. Okay? Now it's easy to see that this W minus 1 and M, sort of a place where motivic Galois group lives, that's the same as actually L itself now. And so this is just because this is pure of negative weight. But now, because of simplicity, you see that the UN is either 0 or M. It doesn't have any other choices. And now, well, 0 corresponds to the case where M is semi-simple. In other words, the extension splits. And then a non-zero, of course, being L, corresponds to M not being semi-simple. So in this case, you have a very nice characterization. Now, here we assume that L was simple. Well, suppose that L is, still pure of negative weight, so just one weight, and that weight is negative, but no longer assume that L is semi-simple. Then, by works of Bertrand and Erdogan, one knows that, M will have a large unipotent radical if and only if this extension here is totally non-split. And by that I mean that if I look at push forwards of this extension along subquotients of L, any push forward along a non-trivial subquotient does not split. So if I look at a non-zero quotient of L, the push forward of this extension along that quotient map is still non-split. So this is when you have two weights and the highest graded piece is the unit object. In general, having two weights, you can reduce it to the statement. You can, without loss, you may assume that the highest piece is indeed the unit object. But what about, how do we get more complicated motives? And by more complicated, I mean more weights, and such motives which have a large unipotent radical. So this is a joint result with Kumar. So suppose that P is negative. Suppose that you have a motive M whose associated graded looks like this. So the highest graded piece is the unit object. And then you have a non-zero piece at weight P, P being negative. And then there's some lower weight stuff. That could be just 0, doesn't matter. But it will be more interesting if it's not 0, then you'll have more than 2 weights. Now, suppose that, so this is how the weight filtration looks like up to P minus 1, it increases, but not necessarily strictly. There's a jump at weight P, and then, up to weight minus 1 it stays fixed, and then there's another jump to weight 0, this quotient being the unit object, and then finally, and then at 0 it stabilizes, it's just M. Now, suppose that WP, so up to this portion, suppose that has a large unipotent radical, and that M mod WP minus 1 has a large unipotent radical. So you're taking this portion here and you're modding that out by WP minus 1. So this object here only has this is an extension of 1 by GER-P. So that's a two-weight object with 2 weights. Suppose both of these have large unipotent radicals. Now, in general, one can construct counterexamples where just these two having large unipotent radicals doesn't imply that M has large unipotent radical. But if you add an extra hypothesis, which we call an independence axiom, if you assume that the associated grid of M satisfies an independence axiom, which I'll say a few words about it, then M will itself also have a large unipotent radical. So this allows you to deduce largeness for M from largeness for smaller motives. Now about this independence axiom, the statement itself is a little technical. So let me just give a condition where the axiom is guaranteed to hold. This independence axiom is guaranteed to hold. So suppose you have a motive with so by weights of a motive, I mean, weights, I mean, places where there's a jump in the weight filtration. So, places where the associated graded is non-zero, weights where the associated graded is non-zero. Now, okay, so you have a motive with some weights. Now, suppose that the pairwise differences of these weights are all distinct. So for example, this example here, I get if my weights are minus 3, minus 1, and 0, pairwise differences would be minus 1, minus 2, minus 3. They're all distinct. if my weights are nicely distributed so that that condition holds, then then this independence axiom is actually guaranteed. In that case, you get this theorem that allows you to conclude largeness for M from largeness from these two sub-objects and sub-quotients of it. Any question about the statement of this theorem? Okay, so now let's see how this can be used to get motives with large unipotent radicals. So the idea is that for two weights, you can get these by making sure that you're looking at non-split extensions, and after that you may hope to sort of patch together these smaller motives to get larger motives. Now, suppose you have a motive that fits in the it looks its weight filtration looks like as we wanted in the theorem. So it's associated is 1 plus non-zero GRP, and then lower weight pieces. Then M gives us a diagram like this. So these are all very natural maps. Here you're looking at the inclusion of WP minus 1 into WP. Next row, you're looking at the inclusion of WP minus 1 into M. And then you can complete the diagram with natural maps, and these quotients would be M mod WP, which is 1, and then this one will also be 1. So this is now the two objects that you want to assume. Our previous theorem, the two objects that appear there are this one and this one. So if this one and this one have a large unipotent radical, and you have your independence axiom holds, then you can conclude that M itself also has a large unipotent radical. Now the question is, going back to this idea of trying to get more complicated motives with large unipotent radicals, the question is, if we have WP and M mod WP minus 1, can we complete the diagram to get an M? If we can, then if we have our independence axiom, if we should make sure our independence axioms hold, then we get largeness results for M. So now the answer to this question of whether a row and a column like this can be completed to the diagram like that are given by Grothendieck's formalism of extension panache or blended extensions, as Daniel Bertrand translates. Now suppose I have exact sequences. So I have an extension of A by B and an extension of C by A. Now, so given ABC and extensions L and N, like that, X group, say the pair of extensions is compatible if you can complete the diagram to the diagram like this, diagram of our interest. And then we're going to say that, so any object M that can be put in the middle of such a diagram, we call it, say it's attached to the pair of extensions L and N. Now, the question of whether, when is a pair compatible, that's, okay, so that's, as I said, the answer to that is given by Grothendieck. So a pair L comma N is compatible if and only if their composition which is now a 2 extension, vanishes, if and only if that's trivial. So going back to my diagram, here this is L and here this is L, and if I compose these two maps, you get this blue arrow, and then so if you look at this highlighted sequence, that's a 2 extension, and the pair is compatible if and only if this is trivial in the X2 group. And moreover, if one of C comma B, one extensions of C comma B, if that group is trivial, then in fact, the object that is attached to the pair is unique up to isomorphism. So in that case, you're getting sort of a canonical object attached to the pair. Now, so I have a little comment here that, the idea of using these blended extensions in transcendence questions that already appears in some works of Bertrand. Now, this is again a result with Kumar. It says that suppose that, so this is an application of the previous result. It's a classification. So for for motives with 3 weights and large unipotent radicals. So suppose that, okay, so there's a P and N in the picture, and there's some conditions on them, and I'll tell you, where why each of these is there. But your goal is to, and A is a pure motive of weight P. You're trying to find a classification for motives M whose associated graded it looks like this. There's a Qn, and then there's an A, weight of A being, so this is sort of an increasing order of weight. There's a Qn, there's an A, and then there's a 1, this A being pure of weight P. So this first condition just says that, this is an increasing order of weight. Your goal is to classify these objects which have a large unipotent radical up to isomorphism. Now, we need some conditions here. See, there's an N being even there that's there because you want extensions of 1 by Qn to be 0. That's where that comes from. So this, I didn't write it down, but this classification is taking place in the category of mixed motives over Q. Yeah, so there you know that the extensions of 1 by Qn when n is even are 0, and that's important because of this statement here. So that's where this condition comes from. And then you're also assuming that n is not equal to minus p. So that's a statement about the weights of this guy and this guy. That's the independence axiom in this case. See, this has weight 0, this has weights p, and this has weight minus 2n. And as I said, the independence axiom, our independence axiom holds as long as the pairwise differences of weights are all different, and that amounts to this condition here. So that's just the independence axiom, in this situation, or what guarantees the independence axiom. Now, assume those, so those conditions on n and p, and again, a pure of a p, then objects M with this associated great and large unipotent radical up to isomorphism that are in one-to-one correspondence with compatible pairs of totally non-split extensions in this product X. So going back to this diagram, here you're putting 1, here you're putting A, and here you're putting Qn. And then you've got extensions of 1A by Qn cross extensions of 1 by Qa. Compatibility is a condition about X2 groups, about vanishing when you compose and you go to X2. But mod, so up to here, this statement doesn't have much more than the first theorem, but the more when you combine it with your Grothendieck's result, but the real added ingredient here is that to get this one-to-one correspondence, you have to mod this out by the action of automorphisms of the 3 objects in the play. And I'll tell you quickly what this action is. So this action looks like this. So here, you've got the 1, and here you've got this Qn. So the action is by automorphisms of this times automorphisms of this times automorphisms of this. And the action here is just, the action of these two is just by twisting these arrows. The action of these 2 automorphism groups is by twisting these 2 arrows. So by composing with the automorphisms. But the action of the automorphisms of A is by, it's anti-diagonal. So you're twisting both of these arrows, but in a way that cancel each other out, and the composition doesn't change. And then you get a one-to-one correspondence. Now, some of these conditions, if you remove, you don't get a one-to-one correspondence, but you still get, so if you remove the independence axiom, you have to leave to make sure that, the totally non-splits are giving you objects with large unipotent radical. But n being even, you can remove, then you're going to lose having one-to-one. But still, you do get a map from this one to this one. Okay, so now I'm going to look at some examples. How much time do I have, Tiago?
10 minutes.
10 minutes? Okay, perfect. Okay. So let's look at some examples here. So let's just, focus on the category of mixed Tate motives over Q. So these are iterative extensions of Tate objects, of those Qns. Now, the reason I'm looking at this category, first of all, so in order to be able to apply this result, or even these ideas, you need to have a good understanding of the X groups in the category, and the X groups in the category of mixed Tate motives are known. Those are theorems. Whereas if you go just mixed motives over number fields. Now those become conjectural. So that's one reason. And the other reason is that, well, you already get some interest. We already get some interesting, questions when you look at mixed state motives. So let's try to see, look at mixed state motives over Q, which have a large unipotent radical, and their associated gradient looks like this. So three-dimensional and with three different weights. And I'm going to assume that you have your independence axiom holds. All of this, breaks down if your independence axiom doesn't hold. Now, and then with that loss, you may assume that your highest piece is the unit object by just twisting with a suitable power of Q1. And then so we want to classify all such motives with the large unipotent radicals, and then the X groups in mixed. These X groups, I recalled them earlier. Remember that if n is even, they are just 0, and if n is odd and greater than or equal to 3, these groups are one-dimensional. And if n is 1, these are Q star. This is be Q star tensor Q with this. So these ones, the one-dimensional ones, are the zeta values, corresponding to the zeta values, and these ones are corresponding to logs. And another very nice thing here is that the X2 groups vanish in mixed state motives over Q. So because of this, because X2 groups are vanish, you don't have to worry about the compatibility of pairs. All your pairs will be compatible. So diagrams can always be completed. Those blended extension diagrams can always be completed in this category. Now, okay, so because we need, remember there's a horizontal sequence and there's a vertical one, and both of those have to be non-split. And by looking at these X groups here, we'll see that parity of n. We see that K has to be odd and n has to be even. If you're trying to get large objects with large unipotent radicals. Now there's two cases here. So again, n is even and K is odd. Now, there's two cases. There's three cases, I guess. But two more interesting cases. Well, one case which is very interesting, and I'm going to focus on that. Now, this is the interesting case that you're looking at, your K is 1. And then your N is even, but not equal to 2. And that's crucial, because if you put 2 there, then your independence axiom fails. So that's not what we want. Now, in this case, so I need an extension of 1 by Q1. So those are, you can take, those are given by Kumar extensions. So you have this extension corresponding to a log R. This is what we're going to take as our vertical sequence. And for the horizontal one, we need an extension of Q1 by Qn, which is the same as an extension of 1 by Qn minus 1, and n minus 1 is odd and at least 3. This is one-dimensional, and you can take any L, which will correspond. This L, we take it any non-zero, non-trivial element there. Put it here. So this is now the period of that would be that zeta and minus 1 talked about. So now in this case, okay, so you apply the previous result, and what you would get is that, okay, so there's a unique object, which I'm going to denote by M and R, which completes the blended extensions diagram, and it has a large unipotent radical because of the independence axiom. And then in this case, see, okay, so let's see what the period conjecture tells us. See, okay, so the motivic Galois group, okay, so there's the unipotent radical, and then there's the reductive quotient. Now that's a GM, it's one-dimensional. Now this one here, see, we know this unipotent radical is large, so this dimension is the same as the dimension of W minus 1 of and M, and see, M was three-dimensional. So this would be 3 choose 2. The dimension of this will be 3 choose 2. This is three-dimensional, and then so in total you get 4-dimensional. Now the transcendence degree of the periods, according to the period conjecture, should be equal to 4. Now let's see what the period matrix looks like. So from this L, you get this 2 by 2 matrix, it's power of 2 pi I, and then zeta and essentially zeta n minus 1 there. And then from this, what did I do? Yes, from n, you get this one here. There's a log R here and power of 2 pi I there. And you know, this is the matrix with respect to a suitably chosen basis. But there's going to be some entity there which is denoted by star, and we don't know what it is. And the period conjecture predicts that 2 pi I, zeta n minus 1, log R, and this star are algebraically independent over Q. And the question is that, so one comment I'm going to make right here is that, so in particular, this says that, you know, 2 pi I, so pi, zeta n minus 1, and log R. So forget about the star, even though really the interesting thing is the star. But forgetting about the star, these three have to be algebraically independent, and that says that. So there's this, you know, this question asked by Euler. So he actually gives a precise formula, which is included in the paper with references. That he thought that perhaps there would be an algebraic relation between these three, actually between zeta of 3 to be specific, pi, and log of 2. And right there you see that, okay, so Grothendieck's period conjecture answers you know, Euler's question negatively. But if one wants to just, you know, disprove that implication just by itself, that the period conjecture, you know, is not compatible with Euler's question, that can be seen in much, you know, that one doesn't have to go to all of this great lengths to just deduce that statement, but one does also see it from here. Now, the really interesting thing here, I think, is this number star, which we really don't know what it is. Now, in the case where this is star, in case where that your logarithm here, log R that you take is log 2 or log 3 or a power of those. So there's this work of Deline that says that he shows that the category of mixed Tate motives over you know, the ramifications at 2 or 3, those are generated by the fundamental group of P1 minus, you know, 0 infinity and mu2 or mu3, and it follows from that work that when R is 2 or 3, this new period here, this is star, I'm calling it a new period. This should be a cyclotomic multiple zeta value, and it can be computed. We didn't do this, but one should be able to calculate this using you know, using a motivic coaction on iterated integrals. But if R is not, you know, power of 2 or 3, then we really have no idea, you know, what the nature of this new period is, and you know, we're hoping to be able to say something about that in the future. Now, I know I'm almost running out of time, so I'm just going to say that, you know, the other case when your k is not 1, so if k is n minus 1, you take your k all the way, go to n minus 1, then this would be actually a dual case to the previous case. So you know, we're not getting anything new really. In the case where your k is between 1 and n minus 1 not equal to those, then here you're putting a zeta value essentially. So you know, a period of a zeta value, and here also a period of zeta value, and then you get a, you know, again, you get a unique object. But in this case, you know, it's not as interesting because from the perspective of periods, it's not as interesting because here these would be mixed Tate motives over Z, and so, you know, by the work of Brown, you do know that, you know, the periods this new period will be a multiple zeta value. And again, one should be in principle able to calculate it using, you know, motivic coaction. So I also wanted to say a few things about the proof, but I'm running out of time, so I'll just stop here.
Thank you. All right, thanks, Payman, for this
My pleasure.
very interesting talk. Any questions for the recorded session? By the way, sorry about my question before. I was thinking about the case of a general field.
Oh no, it was a good question, and you're absolutely right. Yeah, so in the case of a general field, it's not only for number fields.
It's not known, right?
Yeah,
that was my question. Okay. Sorry.
Absolutely, yeah. But for number fields, and especially I worked over Q, right? So that seems.
Yeah. Any question for the recorded session? Otherwise, we can just stop recording. Yes.